Not yet.
Not yet. Okay. Sorry.
Okay, we are live. You can go ahead. Thank you very much.
Well, thank you very much. It's a great pleasure for me to be here and to also find a point of connection with Mikael. We've known each other for many, many years, more than I guess we would like to admit. But most of our collaboration has been through LISA Pathfinder and LISA. We're still connected with those communities, and but we also have, I guess, broadened our interests. So it's great to be here pursuing those other interests. So I'm going to be talking to you a little bit about the optical technologies that we as a community have been developing for LISA and LISA Pathfinder, a little bit of LIGO, and also how these technologies have applicability to other scientific areas. I've divided my talk, just a moment. Yep, I've divided my talk in three parts. I'll start with astrophysics, and I understand that a couple of weeks ago, Carlos Opuerta gave the seminar about LISA, but he didn't really go. He didn't really talk about about how these gravitational waves are measured. I'll tell you how the instruments work, and then also tell you how this technology has now made a stance at the space geodesy community and some of the work that we're doing in my group for these communities. So I'm going to skip the general relativity part because Carlos already covered that at length a couple of weeks ago, which is great. But so now that you'll know what gravitational waves are, let me tell you how they're measured. We used what we call Michelson interferometers. I don't know if you're familiar from that or with interferometers from the first basic courses. But so if you have an array of test masses, as this one here, and these test masses are just sitting calmly in space-time, when a gravitational wave passes, their positions are going to change slightly, as shown in this picture, based on the periodicity of the gravitational wave, of course. And so if you then take some of these reference points, these test masses, and replace them with mirrors that are part of a laser interferometer, a Michelson interferometer, when the gravitational wave passes, the phase relationship between the interfering electric field here at the beam splitter will change, giving you a signal that can be detected by the photo detector. It's a very simple principle. Now, the problem is that those changes in displacement of the mirrors is very faint. It's extremely faint, as I'll show you in a moment. So we have in the US two ground-based detectors, the LIGO detectors, as you probably all know, located in Washington State. They're about 3,000 kilometers apart. And they are basically this same Michelson interferometers I just showed you. However, the arm length of each of the interferometer is about 4 kilometers. So it's pretty long. And probably Carlos covered the reason why. The signal of the gravitational wave is actually strained. So it's it's going to be that change in displacement, that change in position of the mirror over the baseline separation of your detector. So the longer the arm length, then the bigger that signal is going to be, the easier it will be to detect. Now, if we have a very short baseline, then we're making it difficult for us to observe with our current instruments. That's why we want to make them as long as possible. But as you can imagine, there are limitations, mostly technical, on how long we can make them here on ground. The Earth is not flat, right? So that curvature will limit us. Well, there's also, of course, financial reasons on how long you can make them. So as I mentioned a moment ago, that displacement change of the gravitational wave causes on the mirrors is very faint. So faint that the resolution that the LIGO detectors need to achieve is in the order of 10 to the minus 20 meters. So that is extremely tiny. These are the best. And well, we have the one in Louisiana here, the one in Hanford here. I won't go into the details why we use also resonant Fabry-Perot cavities into the arms and so on. That's just to increase our sensitivity of the instruments and such. But this is basically how it looks like. The trace, the noise floors that have been measured in the actual LIGO sites. We have a network of ground-based gravitational wave detectors on the planet, and you probably know this. So the two LIGO detectors in the US, we have one here in Italy, VIRGO. We have a Planning Institute where Michael, Antonio, and I worked. And about 10 years ago, well, more like 12 years ago, LIGO, the LIGO detectors underwent a major upgrade. So all the instrumentation that had been put in place for LIGO that unfortunately couldn't really detect any gravitational waves back then has been refurbished and transferred out to India. And India is setting up another detector that will enhance our coverage. We also have another detector, a so-called third generation detector, CAGRA. Third generation, basically, because we're just advancing the technology. CAGRA is now operating at cryogenic temperatures, and it's also operating underground. So major upgrades that will enhance also the sensitivity, increasing then the volume that we can observe in the universe. You may also note that there are no detectors in the southern hemisphere. This is not necessarily a scientific reason. Actually, for science, we would love to have detectors in the southern hemisphere. And in fact, the detector that is being built now in LIGO was for discussion to be set up in Australia. But unfortunately, for financial reasons, Australia couldn't set that up. And that is the reason why there are no detectors in the southern hemisphere, finances. Most of the countries' facilities are in the northern hemisphere. But we would love to have some in the south. So LIGO covers gravitational waves detectors or observes gravitational waves in the few hertz to kilohertz regime. As you can imagine, that means that the sources are about to collide. So the LIGO signals are lasting only a few hundred milliseconds or a couple hundred milliseconds. So if we're interested in observing bigger dynamics and bigger sources, we need to go to the lower frequencies. And that's where LISA comes in. So LISA is the Laser Interferometer Space Antenna. It consists of 3 spacecraft trailing the Earth around the sun. They're not orbiting around the Earth, separated by 2.5 million kilometers. So ESA was conceived about 31 years ago, when the first proposal was submitted jointly between ESA and NASA. And as you probably have heard recently, just about a month ago, just hopefully launch sometime around the mid-2030s. But yeah, it was conceived initially as a 50-50 partnership between ESA and NASA. Due to some budgetary constraints, 14 years ago, NASA had to drop out. Now they're back in, but with a minor contribution. ESA is really pioneering all this technology. So now, because we're in space, then we don't have that restriction of keeping the arm lengths to 4 kilometers. We can go bigger, and we do want to go bigger. And we went all the way to 2.5 million kilometers. And that's basically just a trade-off of how far can we get them, all the instrumentation needed for that to maintain that long baseline. And you can think then, well, what is the resolution that we need now that we have a longer baseline? So LIGO needs to measure 10 to the minus 20 meters. What are the requirements for LISA? Well, LISA needs to measure picometers. So that's still very challenging. It's about a 100th of the diameter of an atom, but well, definitely makes it simpler to detect than what LIGO needs to achieve. Now, the big difference between LIGO and LISA is that LISA, once you launch the satellites and they turn on, they need to work. There's no way we can send anyone there to tweak a beam splitter, set up the alignment, open up the vacuum chamber, and go in and realign the test mass as we do in LIGO. If anything happens with LIGO, in fact, right now, the 4th observing run of LIGO was interrupted. It was a planned interruption for a few months to do some upgrades, and then we'll restart probably at the end of March again. But we have that ability here with LIGO. We don't have that with ESA. It has to work. So some people may ask themselves, or they ask me often, why is it that it takes so long to to develop these missions. And, we test everything extensively to ensure that they're going to work once you launch them. That's part of the reason. Now, we need to measure picometers. As you can imagine, all these three bodies are not staying there at a baseline separation of 2.5 million kilometers to the picometer. Those satellites will be drifting, and they drift about 1% per year. So that is 25,000 kilometers. That's way, that is very different than a picometer. Now, the reason that this works is because those 25,000 kilometers happen in the course of a year. It falls outside our observation band. Yeah. So in the band, and in the bandwidth where we're observing gravitational waves between 0.1 millihertz up to 100 millihertz, we can achieve that picometer sensitivity. This is the sensitivity curve of LISA. As you see, we're in the, sort of 10 picometer level here. LISA consists of 3 identical spacecraft. All these spacecraft have this sort of Y structure here containing, each one of the payloads here is identical. They carry a telescope, an optical bench, a gravitational reference sensor, which is sort of our test mass, our black dot in that diagram that I showed you earlier, and something that we call the MOSA, the moving optical subassembly. So this Y structure needs to be articulated because, as I mentioned, the baseline separation of the spacecraft is going to be changing by 25,000 kilometers. That means that we need to act on that angle to point the laser to actually hit the spacecraft that is far away, right? Because that angle is going to be changing. The laser beam inside the spacecraft is about 2 millimeters in diameter, and it measures, basically, it tracks the motion of the test mass that is ideally only moving because of the path of a gravitational wave. In reality, we know there are many other disturbances, and we have implemented and tested this concept with LISA Pathfinder. In order to send the laser beam across 2.5 million kilometers, we know that the laser beam is going to expand, but we want to minimize that divergence as much as possible. The way you do that is by increasing the size of the beam, basically increase what we call the Gaussian beam waist. So you want to launch out of the spacecraft a laser beam that is as large as possible, but the spacecraft has a finite size. We need to make, again, compromises in that technology that we're going to have to set up. So the telescope has this piece here is called the LISA telescope, has an aperture of about 30 centimeters. So the laser beam coming out of the spacecraft has 30 centimeters. By the time it arrives at the far spacecraft 2.5 million kilometers later, has a diameter of 15 kilometers. So, of course, the spacecraft is not out, and we need to perform this picometer level interferometry with about a few hundred picowatts of power. That is challenging, but it's been demonstrated in the lab. Now, the reason why we have that little power is because the stable lasers needed for LISA can only output between 1 and 2 watts. That is the technology limitation that we have. Now, you can also see that this telescope piece here is right in the line of sight. So it's right in the path of the interferometer. So we need to maintain that large structure here stable to the picometer level. So this is about the instrument, the prototypes that we're testing now are about 40 centimeters by 70 centimeters. So it's a meter scale device. And this is actually an instrument that is being built by NASA. We, together with the University of Florida and the NASA colleagues, are testing now some prototypes of the LISA telescope. As part of that, my group is developing what we call the optical thrust interferometers. So this is the first time that an instrument of this size is developed that requires this level of stability. So we don't know how it's going to behave. We need to make sure that it's going to be stable to that level. So these optical thrust interferometers are Fabry-Perot cavities, some type of interferometer, if you're not familiar with that. And we've built them in a compact fashion. And they are capable of just being mounted around the telescope having basically very sensitive interferometers here that will tell you what is the distortion of that structure with temperature, for example, and other effects. Of course, these instruments, if we're going to be evaluating the stability of the telescope, they also need to be good to the picometer. And luckily, we have demonstrated in the lab that they're already meeting the picometer level requirement. Actually, the more recent measurements are better than this. So if we need to attach them to the LISA telescope, we can assure that we'll have an instrument that is good enough to evaluate the performance of the telescope. So as you see, LISA is a very demanding mission. It's very challenging. That's why NASA and NISA decided many years ago, about, I would say, way too long ago, to launch LISA Pathfinder, to test three very specific points that would make LISA possible. One is the residual acceleration noise of the test mass. We want that test mass to move only, to change positions only at the path of a gravitational wave. So that means we need to shield it from everything else. And that everything else gives a residual acceleration noise of 10 to the minus 15 meters per second squared per hertz. The other thing that we needed to test is picometer level interferometry with free-flying objects, because we can test picometer level interferometry here on ground, as I just showed you. And then, of course, all the actuators on the spacecraft to ensure that we can achieve this residual acceleration noise. Those are what we call microneutron thrusters. So that was the idea of LISA Pathfinder, basically to take one arm of LISA, shrink it down to a single spacecraft of about 38 centimeters, and then test these technologies. LISA Pathfinder was never meant to observe any sort of gravitational waves. It was only intended as a technology demonstrator. And so we flew interferometers, we flew microneutron thrusters, and the test masses, of course. It launched on December 3rd, 2015. And this little video from ESA will tell you basically what it does. So it was launched to the Lagrange point 1. You're probably familiar with that. It's a very stable area gravitationally, 1.5 million kilometers from the Earth. And so you have the two test masses, ideally following geodetic trajectories, separated by about 38 centimeters. We have an optical bench carrying 4 interferometers, measuring the motion of one test mass with respect to the optical bench, and then also the differential motion between the test masses. Each test mass is enclosed in vacuum enclosures. That is basically just to shield it from any impurities and dirt that flies with the spacecraft. That would be a problem in those systems. The entire experiment sits at the center of the spacecraft. All the other instruments are around, solar panels here on top. And when you have any sort of disturbance coming in, the little microneutron thrusters are firing, wiggling around the test masses, making sure that the test mass is standing still, and the one reacting to the disturbance is the spacecraft. That is what is called drag-free flight, and that is how LISA and LISA Pathfinder worked. So this is the optical bench, the flight version of the optical bench for LISA Pathfinder. We designed it at the Max Planck Institute in Hanover. Glasgow built it, did the final design iterations and built it with collaboration from the University of Birmingham on the photodetectors. This, of course, had to be qualified. And it's very scary when you see this beautiful piece of glass being shaken this way. It was, I guess, now about 13 years ago, Mikel, that Mikel and I and others, I don't see Victor here, but others from the group here were at the facility of IABG in Germany, testing the integrated LISA Pathfinder satellite. So we were there day and night, gathering data, testing all the components. Mikel and his team were there testing the temperature sensors, the diagnostics. I was there testing the interferometer. It was not a quiet facility. This It's not a facility that would necessarily stands out for stability, but we were still able to measure the picometer level resolution of the interferometer there, and everything worked out well. Then we launched it in 2015, and about 4 months after launch, we had significantly surpassed the LISA Pathfinder requirements, and we're already scratching the LISA requirements a year later. Once we had understood all the issues on the interferometry, we significantly surpassed the LISA requirements across the entire spectrum, which is a gigantic success. So we know exactly what is limiting us at each piece of the spectrum, which was the goal, and now we know what to do for LISA. There are still points that are under development that were not tested in LISA Pathfinder, such as the telescope. That's why we're doing that now. Now, it turns out that about also 15 years ago or so, the community of space geodesy in the gravitational wave community started to talk about taking some of this technology for geodesy applications with the GRACE missions. So GRACE, for those of you that are not familiar with it, stands for the Gravity Recovery and Climate Experiment. It is effectively an Earth observation mission. It consists of 2 spacecraft on a polar orbit, and they basically measured the gravitational fluctuations of the Earth. So these 2 spacecraft, basically the way they work, they're flying separated by about 200 kilometers. When they observe a so-called mass anomaly, a mountain or something like that, you know, the first spacecraft will feel that lump of mass. It will get accelerated towards it. The baseline separation will change. At some point, the second satellite will see that too, get accelerated towards it. The baseline separation will shrink. And if you play that game across the Earth, then you get an idea of what the gravitational map of the Earth is. Now, if you do that game over years, then you see how that gravitational map is changing. And now, what does it tell you? It tells you how the mass on Earth is being redistributed. What happens with all the water mass that is melted from the polar ice caps? Where is it going? It'll help you identify areas for flooding and such. So it's a very insightful and by now important mission. The first was doing this inter-spacecraft metrology with a microwave instrument, a microwave interferometer. Well, it turns out that the microwave interferometer at that time was being a limiting factor for how well we could do this observation. So, well, in LISA, we're doing, and the microwave interferometer can measure this distance with micrometer resolution. For LISA, we're doing picometer. So we started talking with this community to actually implement a laser interferometer that would do that metrology. And that was actually done for the second mission, GRACE Follow-On, that was launched in 2018, which to have the same baseline, and the laser ranging interferometer was added to the mission as a technology demonstrator. And it has been very successful. It has been able to measure the spacecraft separation with nanometer resolution. For this mission, we don't need picometer resolution. And because of some technical aspects, the limitation there is about 10 nanometers, mostly driven by laser frequency noise. But that is sufficient for this observation. It has operated for several years successfully. And for the subsequent mission that is planned to be launched in 2028, the baseline will be a laser interferometer. We're scratching completely the microwaves. So that has been a giant success. Now, for these missions, there are other instruments now that are the limiting factor, no longer the inter-spacecraft metrology, but actually the accelerometers. So GRACE, the GRACE satellites fly accelerometers in order to detect non-gravitational forces. So the spacecraft are effectively the gravitational sensors, but as you can imagine, there's drag acting on them. There's other effects that will act or will give you an acceleration signal that could look like gravity, but it's not. So you want to measure that and subtract it out from the signal. And these devices have failed in both missions. Not completely. They still operate, and we can still get good signs from them. but they're operating suboptimally. So there is quite a bit of effort right now ongoing in the community to develop new types of accelerometers that can be used for these observations. And these accelerometers can also be operated on ground. It turns out that there's a great deal of information that you can achieve doing gravitational sensing on ground or planetary sciences and such. And the reason for that is that, well, gravitational sensing help us identify also where we are and where we're going. So right now we rely on our GPS sensors to tell us where to go if we want to, if we're moving somewhere. But we know that these signals can be jammed. However, gravity cannot be jammed. We can, if we have good enough sensors, we can actually tell where we're going just by looking at the changes in gravitational acceleration. This is also very important, for example, in the observation of detection of aquifers, geothermal exploration, minerals, oil, underwater and underground navigation, where you don't have any access to GPS. And as you can imagine, of course, certain defense applications as well. So the types of instruments that have been used so far are enormous. So this is just an example of the gravitational sensors, or the accelerometers or gravimeters that are currently used to achieve those sensitivities. So in my group, we're making it a point to miniaturize these technologies, not just for ground-based applications, but also for applications like rays. And the concept of the accelerometer that we're doing is so-called optomechanical. It's based on this very simple mechanical resonator. You have a test mass attached by two leaf springs to a base. And I guess the trick that we're pursuing is by selecting monolithic pieces of material and fabricating that structure from that monolithic piece. We're not fabricating the components individually and then gluing them together or attaching them together or welding them together. We're just etching out. Doing that, we basically inherit the properties of that material. Low mechanical losses are the key in this case. Low mechanical losses basically translate in high mechanical quality factors, which basically will give you an idea of how good that mechanical resonator will be for acceleration sensing. This, for example, this is a 5 Hertz resonator, a very low resonance frequency, but also in a fairly compact format if you compare it with the instruments that I showed you earlier. This is a US penny, just to give you an idea of the size. Now, of course, the acceleration sensitivity is not going to be just limited by the performance of the mechanics. You also need to observe that test mass displacement, and you want to have a good sensor for that. We're developing the little interferometers that we're matching with them to measure that acceleration sensitivity. And just to give you an idea of what we're pursuing, this black trace is effectively the performance we're hoping to achieve with these sensors. The dashed lines here are the trace accelerometers. This green line here are some seismometers that are currently used on the LIGO sites to stabilize their platforms. The purple one here is I guess, derived sensitivity of the InSight seismometer on Mars. And this blue trace is what we've measured so far in our lab. So we're getting there. We're about a 1.5 to 2 orders of magnitude away from where we want to be. So let me tell you why. Well, we're also developing the little interferometers that go with that. The sensitivity of the interferometer is the one really limiting us at the moment, mostly because despite of the fact that LISA Pathfinder demonstrated it, it took us actually a great deal of, let's say, interesting technologies to achieve that sensitivity of the interferometer. Basically, lots of good tricks and control loops, effectively. If you want to miniaturize things, you want to actually avoid complexity. But so right now with the system we have, we're being limited by some fiber noise. We're about an order and a half of magnitude away from where we want to be. And we're trying to implement some other noise mitigation strategies to achieve our sensitivity goal. So this is our test setup in the lab. I mean, when you develop an instrument, you do some testing here in the lab as extensively as possible. This is our setup. We have a vacuum chamber on top of an optical table on pneumatic feet on a separate foundation of the building. We have purchased commercial seismometers to compare the signals that we're measuring with our system. This is our little accelerometer. There's a lot of optomechanics around that, as you'll see in a couple of slides, we replaced and integrated into a little box. This is the little interferometer. And this is a very busy plot. So let me tell you briefly what this is about. The black trace here is the measurement straight out of our sensor. So when we measure, let's say, overnight acceleration with our sensor, this is what we get here. And at first, we were scratching our heads because we didn't understand what was going on. Even with, let's say, suboptimal performance of the interferometer we have at the moment, and the characterization of the mechanics that we've done, which is actually pretty good, we were supposed to measure already in the lab acceleration noises, noise floors that are better than this. And we kept observing this level. We kept observing this structure, and we didn't know what it was. We're not geophysicists. We're talking to people. We started digging the literature, and it turns out that this feature here is something that is called a microseism. Maybe some of you are aware of this. We weren't. We had to find out. And when we run measurements concurrently with a seismometer, the seismometer is the yellow trace here. They're right on top of each other. So basically, all of this here is signal. It's real signal that we're picking up in the lab. And let me tell you what this feature is. I mean, you're fairly close to the coast here. And when you go over the weekend and sit at the beach and, you know, maybe enjoy a glass of wine, and you see the waves crashing at the coast, recoiling, coming back and crashing at the coast, those crashes basically create acoustic waves that propagate across the landmass, creating interference, so interfering with each other, giving you signals at the 10th hertz to a hertz. So if you think of it, if you picture yourself there on the beach, those crashes come at a period of, you know, a second to maybe 10 seconds. And that's exactly this. Now, we were not expecting to observe that because we're 210 kilometers away from the coast in Texas. I just transitioned from Texas to Arizona. So we did all these measurements in our labs in Texas. So we were really not expecting to observe this, but that's actually what's limiting us. Now, there are many other traces here that I don't want to bore you with, but, you know, we're also picking up, for example, changes in the atmospheric pressure. So, you know, when the weather changes, the atmospheric pressure changes, the pressure in the room changes, and that change in the air pressure in the room applies a force to our vacuum chamber here. And we have inside this vacuum chamber a little suspended platform. Perhaps you see here one of the steel wires suspending that platform, and that starts to swing very slightly, but that's something that is limiting us at 10 to the minus 4 hertz. And it took us, again, some digging to realize that. Now, one way that we decided to test the noise floor of this system was by basically anchoring the test mass, putting a little stop on the test mass and preventing it from seeing signal. And when we do that, then we get sensitivities in the order of a few, well, 10 picog's, 8 picog's above 60 millihertz plastic. As you can see here, we've also now integrated all those optomechanics into little fiber injectors and couplers. We've put everything into a little box now that it can be transported. It's not really ready to be transported, but, you know, we're working on it. But so far, we've been doing all these tests with this uniaxial device. NASA was, for a GRACE mission, was interested in our turning this uniaxial device into a triaxial system. So we came up and designed a triaxial device based on the same concept of these parallelogram flexures. This is the top layer. We call it the XY stage because, you know, it measures in X and measures in Y. There's still one axis left that we need to measure. We conceived that as a drumhead resonator. that you can see here. This is the X, the Y, and the drumhead resonator is a completely different topology. But we were able to design it with very similar characteristics in terms of resonance frequency, mechanical losses, and so on. And we have finally fabricated it. We received these pieces, I think, back in early November 2023. And we're now already starting integration of this triaxial. This is a picture that we took about 3 weeks ago in the lab. So we're making some progress. You can see here the little interferometers. Also for the out-of-plane resonator that you see here, we're using components such as a pentaprism that basically diverts the laser beam straight at a 90-degree angle and such. So just everything to try to maintain a compact format. Here again, and just to give you an idea of size, is a US penny. It turns out also that this XY system proved itself to be very interesting, because we realized that if you have arrays of those dual accelerometers and set them up as a cube, you not only measure acceleration or linear accelerations along the three axes, you can measure the angular accelerations along those three axes. So when you have linear acceleration and angular acceleration, everything in one instrument, you have a full inertial measurement system. And for missions like GRACE, or for planetary missions, for example, in Venus, where you don't have access to star trackers, you need a way to navigate and to understand what's happening there. So the surprise for us was not the case that we could achieve sensitivities comparable to GRACE in linear acceleration. We knew that. The surprise to us was that the angular sensing capabilities of such a system are significantly better than the fiber gyros that are currently flying. So that was a big surprise, because when you measure linear angular acceleration, you need to do two integrations to get angle. The fiber gyros measure angular velocity, so they only do one integration. But because of the fact that these accelerometers are so sensitive, you can achieve orders of magnitude better sensitivity than the fiber gyros above a millihertz, which for many navigation purposes is sufficient. So that was very interesting to us. So we've proposed this concept to NASA for not just Earth observing platforms, but also for planetary seismology, for example. You can deploy something like this on Mars, or, well, now that we're trying to go back to the moon, you need to monitor the activity in the moon. So you can deploy these compact devices, these little boxes around the moon, and do your measurements. Some people at JPL approached us because they're interested in flying balloon missions in Venus. Now, the Venus atmosphere is very thick. It doesn't give you access to observe the stars for star tracking and orientation. So you need to rely on something like this to be able to navigate. So that's very interesting. Now, the reason why I'm here today is because after working for so many years on LISA Pathfinder and LISA with Mikel, we finally found a way to do something else too. And so Mikel was very gracious to include us in his idling proposal that he just won, I think, a couple months ago. You were notified, you submitted it the middle of last year. And that is to develop new technologies for spaceflight and science. We want to do science based on optomechanical resonators. So Mikel's group is top-notch in temperature sensing. Now they want to take advantage of these new capabilities of developing optomechanical resonators and use these resonators now to sense temperature to the nanokelvin level, which is unprecedented, particularly on payloads for spaceflight. Now we also want to provide our expertise, because aside from, let's say, this, well, they're still compact, these pieces are fairly macroscopic. We have started microfabrication of optomechanical resonators, as you can see here. And we're looking into developing those microresonators on chips, silicon chips, that are equipped with waveguides to measure the motion of those test masses. And the reason to do that is because at the end of the day, you get very high sensitivity, but you also facilitate how these instruments are produced. and also improve the reliability of them. There's no more, or there would be no more placing of compact optical objects in alignment that is honestly very tricky. You just, in the same chip, fabricate the resonator and the waveguides that would measure the motion of the test mass. That is our goal. And of course, we want to do within this project some technology transfer between what Mikel is doing and what we are doing in Arizona to develop new types of sensors for scientific missions. So this waveguide, for example, we've done some simulations. It's based on whispering gallery modes. Basically, you inject light here. There's evanescent coupling of the light into this ring resonator. Depending on the properties of the ring resonator, the light will make several turns there and increasing the sensitivity. And at some point, it's going to come out, and we detect that. When the test mass then moves, there's going to be a change in the index of refraction because of the stress. And that is your signal. That's basically how it works. We've done some simulations in console about the dimensions of the waveguide and its performance. We've also done some simulations about the conversion factors, and we do expect to see a significant signal under the presence of micro G's or less acceleration. We're working with low finesse, basically low. We're starting with just a few turns. We don't want to have the light circulate there too many times at the moment, but we're looking into ways of increasing that. Now, if you indulge me one more minute, let me tell you a little bit about what we do else in my group. We're not just working on these little interferometers or this, let's say, macroscopic optomechanical acceleration sensors. We're also looking into how to pair or develop new types of quantum-based gravimeters using atom interferometers and optomechanics, hybrid systems. We're looking into new types of dynamic lasers. There are ways where basically this resonator can itself be a laser, and as the test mass moves, then it'll change the frequency of the emitted light. We're looking into implementing these new technologies in future applications of LIGO. For example, Cosmic Explorer, the Einstein Telescope, LIGO Voyager. LIGO Voyager is an interesting one because it is expected to operate at cryogenic temperatures. So it is the Einstein Telescope. And the problem with those platforms is that there are no sensors at the moment capable of measuring accelerations to these levels that can operate in cryogenics. So maybe you remember a few slides ago, I showed you that there was a trace there where we're comparing our sensitivity with the sensors that are being used on LIGO right now. Those are seismometers that are about this big, but they're not vacuum compatible. So what the LIGO community is doing now is they're taking those cooler size systems, they're putting them into pressurized boxes that end up being the size of this table, weigh about 50 kilograms, and that's what you can put in vacuum. So that is not really practicable. So we want to create inertial sensors that can actually be compatible with not just with vacuum, but also with cryogenic environments. And lastly, let me acknowledge my team because they're actually the ones doing all the work in the lab and giving me nice pictures for you to see today. So thank you so much. I'll be happy to take any questions.
Thank you. Any questions?
Okay. Thank you very much for the talk. At some point, you mentioned that the LISA Pathfinder used a different, let's say, configuration of the interferometer to discuss some aspects and some challenges. Now, the challenge of having them at far distances is the one that needs the accelerometers, better accelerometers, because I think I lost this.
Okay, yeah, let me go back to that. So I think we can go here. So what LISA Pathfinder sort of demonstrated was this local interferometry. So the LISA interferometry is actually broken down in three pieces. So actually two. So you have the long interferometer, and then you have so basically from telescope to telescope, and then you have from telescope to optical bench and test mass. So LISA Pathfinder demonstrated the optical bench to test mass. The big item missing now is the telescope. Now, of course, in that gigantic interferometer, there are 2.5 million kilometers of nothing, just vacuum. So we're focusing our testing on the telescope itself and the metrology of the telescope to the optical bench. That is where the community is focusing. So ensuring that this portion here is picometer stable.
Yeah, because actually I was thinking that maybe there are effects like solar wind fluctuations, radiation pressure being a little bit different between the telescopes, that would require some kind of high precision accelerometer to understand individually what's happening with each telescope.
So that is actually a very good point. In fact, we have been discussing that, but not so much for the mission itself, but for the ground testing. So ground is very noisy. Something that Florida is doing, for example, is setting up a test bed with a big vacuum chamber where we can apply a significant temperature gradient. Because, you know, part of the telescope is going to be inside the spacecraft, part of the telescope is going to be closer to free space. And you're going to have a significant temperature gradient. Now, having a temperature gradient may not be the real problem. We need to verify that. We don't expect it to be a big problem. Temperature fluctuations would be the problem. Now, if the gradient is big enough such that the telescope deforms itself, you know, it is a focus using optic that could potentially change the properties of the laser beam and affect the rest of the metrology. That's why we need to do the thermal cycling here on ground and test that, or not just cycling, but also the mimic the temperature gradient that we would expect. Now, temperature fluctuations would be a problem, because if they're big enough, then the telescope is going to be doing this. And if they're big enough, they could violate the picometer necessity, let's say, that we have. Yeah. Now, in order to test that on ground, sure, we will have vibrations coupling into the system, and we're not going to know necessarily if it's the telescope deforming because of temperature or because of the vibrations of the vacuum pumps or something else in the lab. And for that, you want to have accelerometers placed in the facility. Yeah.
Okay, that's something to your question, and indeed the solar wind effects. It's not an acceleration, but it's an acceleration in the sense that the fluctuations of the interplanetary will affect the test mass motion. So, for example, when we do the test mass to be completely mass non-magnetic as possible, it has some accessibility. The fluctuations of the but that we do by monitoring. So we first continue with the key meters in the spacecraft. We have about 6 spacecraft, so we team total meters to monitor. But that is a value in our group is starting. And these fluctuations and this data is about to publish the results that we don't use with this setup. This is the picture, in fact, is important because you don't have in a space seismic noise and things like that, but the solar wind acts like that. It's a turbulent medium, and if you couple to that, then you will have something that makes sense. I have a question for Felipe, because I saw the optical truss, and when I saw this and together with this picture, the last part, let's say the cavities at the end, they are in contact with the space directly. So this is let's say in terms of semi constraints or this, because that would be very, very, I don't know if that imposes restrictions, requirements on this cavities.
Well, it'll be basically similar restrictions and issues that you would have with the telescope itself. the way we went ahead and designed the optical truss, as you see here, well, maybe here, this is just blue tape, by the way. It's just tape protecting the surfaces, because these are here polished surfaces, so you can do hydroxide catalysis bonding to the structure itself. The telescope is being fabricated out of zero Dur. And so are these pieces here. They're zero Dur, so you can just do bonding straight into the system. So all of that, yeah, I mean, temperature would couple for sure. Now, the distortions that you would expect are very similar to the telescope. It could also potentially be that temperature changes will affect the little optics that are here inside. And, that will change the mode that is resonant to the cavity. But actually, we've found that our design is surprisingly resilient. So these pieces have been, these cavities have been designed to be at a separation of 70 centimeters. So the telescope itself, we have been testing them on an ULE-based breadboard of 20 centimeters. So significantly different than the baseline separation they've been designed for. That changes significantly also the mode that is resonant there, but still works well. So it is underperforming, let's say, because of that change in separation, but it's still good enough. So you would have something similar where there will be a slight change in the mode, and you may end up having the non-ideal mode matching for it, but it would still work. Yeah.
Some little question. I think I missed that part in your presentation. What are the requirements for the test mass? What is the typical test mass?
That's a great question. So there are many requirements. I guess one of the biggest requirements is being non-magnetic. You don't want the test mass to move because of magnetic forces. So that's why the material that they're made of is an alloy of platinum and gold. I don't remember what is the ratio. Is it 80% platinum and I think 70? Okay, yeah, something like that. To have a very low overall magnetic moment. Now, of course, these are metal pieces. They're going to get charged. So there are actually 3 items that the US is delivering for LISA: the telescope, the laser system, and the charge management system. Those are little LED UV lamps or UV LEDs that discharge the test mass when it starts accumulating charge, because that electrostatic force could also be a problem. Those are, I would say, the biggest ones, the biggest requirements. Yeah. Yeah.
Yes, localizing the source of
That Carlos, you probably know that better than I do.
The localization.
Yeah.
The best milliard seconds.
Milliard seconds. Yeah. Okay.
The best.
Yeah.
But it's not very good. In general.
Yeah.
Yeah, in the previous mission that you were on the spectrum, in the data that it's been predicted mission, the function of the values for science seems to be aligned that is several hundred better. Is the one used for the science or just
Yes. Yes, exactly. So the community has been using the interferometer data for the science. That's right. And actually, I forgot to mention, so because the title of my talk mentions planetary sciences too. There was some years ago a mission called GRAIL, which is basically grace around the moon. So these type of technologies are now very interesting for studying and understanding planetary systems. There's been discussions about doing something similar on Mars. Yeah, but certainly deploying seismic sensors on Mars, the moon, and other objects is interesting as well.
I have a question on the acceleration. So I saw that some of the lines that had a strong slope. So that means that at some frequencies, there is very few noise, but at other frequencies there is it's much noisier.
Correct.
I guess that there is some limitations on the accelerations of the platform that can be tracked with this, or
Well, yeah,
if
of
it's-
course.
If it's moving very fast, maybe, or very slow, I don't know.
Well, yeah, so let's look at this. So this line here is a millihertz. So integration times of about 1,000 seconds. So if you're relying on inertial navigation over 1,000 seconds, you're going to get very good sensitivity, better than what you would get with a fiber gyro. Now, this tells you how well you can measure angle. These are actually radians. So it depends on how well you need to know your orientation over time to be able to say if this is going to work out for you. Now, this slope here is just the way it works. I mean, you're measuring angular acceleration. To get angle, you need to do that to integration. So you're going to get that slope anyways. You're going to get also intrinsic drifts because it's a macroscopic object that just changes over time. That, in fact, is the reason why we're looking and have other efforts ongoing to do hybrid systems with atom interferometers, because atom interferometers do not have that drift. They're absolute systems. So, they would basically take care of this drift here and give you better.
But basically for short time.
Yeah.
Acceleration for short periods of time, it works very well.
Yeah.
But if you want to navigate many days or many hours, then
yeah, at some point you're going to need some type of let's say reset, and yeah, and that's how I guess all navigation systems work. So for example, in GRACE or in space missions, you have the star trackers. Star trackers don't have very good sensitivity at high frequency, but they're fairly good over long periods of time. Now, because the spacecraft is maneuvering and doing dynamics that are faster than this, you do need other sensors that can tell you what your acceleration orientation is at higher frequencies. So that's why you fly them. But every so often, basically, you use you rely on the star trackers to reset that system. Yeah.
Other questions? Thank you very much.
Thanks.
Sorry, I think there is any question from the online people? No. So, well, thank you.
Thanks.
Thank you.